Hello, everyone. Thanks for listening my presentation today. My name is Annan from the Emerging Device and System Group. Today, my presentation topic is time-of-flight technology for scalable depth sensing from device to system level intelligence. Depth estimation technology is a kind of technology that can recover the distance of the object. According to the type of the sensor we used, depth estimation can be roughly classified into three categories. The first category is based on RGB sensors, such as the monocular depth estimation and stereo vision. This kind of technology recover the distance by geometry. The second kind of technology is the direct time-of-flight based on the single photon avalanche diode. It is also called LiDAR. Topic of our today. For indirect time-of-flight, we will emit a light and then receive a light. We will calculate the phase difference and then recover the distance. Let's look at the technology in a detailed way. In an iToF system, we have an IR emitter and a sensor. This emitter will emit a light wave signal, and then after the signal is reflected by the object, there will be a reflected signal to the sensor. Definitely, there will be a phase shift between these two signals. As long as we can calculate the phase shift, we can finally get a distance output from this equation very simply. It has the characteristics of low computation overhead, close range, relatively high resolution, and accuracy. The right side shows a very good example of iToF based on the Microsoft Azure Connect DK. With this iToF sensor, the system may estimate the people's pose, and then the people can fly in the virtual world. And this is a real video recorded by me in a tourism. For the iToF sensor chip, it contains many photonic demodulator in every pixels. Please allow me to give a very brief and short principle introduction. For emitted signal, ETE, we will get a similar signal in the sensor chip called RT. The RT is a reflected signal. After we get a reflected signal RT, it will generate signal electrons inside the chip substrates. These electrons will then be modulated by a demodulator and also integrated in the sensor node. This process is illustrated by this equation. With different modulation phase phi, we can get different S phi, and then by using different phis, we can get the phase shift by using this equation. In the simplest case, we only need 2 degrees. We can calculate the entire distance as shown in this equation. This is the simplest explanation for this technology. What is the current problem for iToF sensor? Let's look at the smartphone as an example. In 2018, Sony became the world's first company that can massively produce iToF sensor. At that time, it became the peak of iToF technology. Many Android flagship phones, such as Huawei Mate 20 Pro, Honor V30, includes iToF sensors. However, the change happened at 2020. Apple includes direct ToF LiDAR scanner inside their iPhone 12 Pro. Instead of iToF, the biggest smartphone company in the world chose the DToF, and then all the other vendors trend-to-shift technology. In 2023, things become even worse. A very strong competitor is the AI-based depth estimation. For example, the foundation stereo from NVIDIA has achieved very good performance. Whether we need a depth estimation module inside the phone is a question mark. How about the entire market? For the entire market, we can develop the applications into 3 tiers. For the first tier, there is already no places for the iToF sensors. In the tier 2 and tier 3, iToF can occupy a large number of it. However, the market size of tier 2 and tier 3 is not as large as the previous one. Therefore, iToF is growing slowly as it is not in the tier 1. Although the entire depth estimation market is estimated to be 200 billion Chinese yuan, we have to say that iToF is still going the slowest and cannot earn too much profit for the market. What is the reason? Is iToF not accurate in the ideal cases? The answer is no. Actually, if you look at the survey, the accuracy of iToF is very high now in a complicated process. Modulation contrast is a value that can directly proportional to the depth precision. If you look at that value, it is almost close to 100%. The thing is, the development of this technology has been saturated after 2020. Before 2020, every year there was at least 2 iToF papers in the ISCC image sensor session. However, since 2022, there are few iToF papers inside the session. What is the current challenge? From my perspective, it's mainly because of the high cost, intrinsic limitation, and stress from AI. First of all, currently the cost for the iToF sensor is too large. Let's look at Samsung Pixel as an example. In this Pixel, they include a lot of advanced complicated process technology, including the backside illumination, deep trench isolation, backside scattering, thick SI with light doping, and doping gradient. This kind of process is very complicated and has a very high price for massive production. The second problem is the intrinsic limitation. iToF are sensitive to the multipass interference and background noise and short noise. This limits the upper bound in the real cases. The second one is the stress from AI. The transformer-based foundation model has achieved very good performance, as shown in the depth anything figure. Compared to the AI method, traditional ToF has no advantages in cost with the help of NPU, and no advantages in quality in terms of whole. The AI-based depth estimation is blooming. The best example is the foundation stereo in 2025. I have proposed 3 solutions in terms of these 3 problems. Let's look at the first one. First of all, I need to give a more detailed illustration for the modulation contrast. In iToF, modulation contrast refers to the ratio of the modulated signal to the background, which directly determines the signal-to-noise ratio and depth accuracy. In ideal cases, as shown here, the modulation signal will be perfectly aligned with the light, and therefore, the NU we receive will be 0 for ideal demodulator, and therefore, MC is close to 100%. This is the upper bound. For mainstream demodulators, it can be roughly divided into 3 cases. The first one is a current-assisted photonic demodulator. It has high power due to its whole current. At the same time, it can have a high modulation contrast. The second one is a traditional pin photodiode. the modulation contrast is lower due to the slow diffusion inside the PPD. The third one is a gate-based photonic demodulator. It has medium modulation contrast due to the competing between the two gates GA and GB. Normally, the MC of CAPD is larger than GAPD and larger than PPD. And for power, the GAPD is barely equal to PPD and smaller than CAPD. In our work, we want to propose a work that has a larger modulation contrast compared to CAPD and more larger than PPD. And for power, we want to maintain the small power. To get the real case, we do the simulation of GAPD in a typical 0.18 micrometer standard CMOS process. The sensing node is set to 3.3 volt for initialization. After the initialization for DA and DB, we start to modulate the GA and GB, also with 3.3 volt. These two figures shows the potential and the electric field of this structure. To further see the charge transfer, we add an optical wave that is 850 nanometer with an intensity of 2.5 milliwatts per square centimeter. This is a normal case of ToF sensing. As shown in this figure, although the charge can be carefully transferred with the collecting, assigning, and storing process, there are still many stray electrons due to this competing between the two gates. These stray electrons go to the undesired terminal GA and then directly lower the modulation contrast. To solve this issue, we propose a gate-assisted photonic demodulator with contrast enhancement. An asymmetric electric field can be generated inside our structure. As you can see, this is the potential of this structure. The barrier height for this structure, for example, at the edge of region 1 with a depth of 0.5 micrometer, has been increased 33% compared to the original structure at the depth of 0.5 micrometer. If we zoom in with electric field and charge transfer and plot out the lateral current of this structure, we could see that the competing mechanism for the GA and GB is clearly suppressed due to the N plus PVL region and also the gate. Most of the photogenerated electrons are collected by our desired detector node. In this figure, the blue one is the direction we want. If we quantitatively analyze the result in this regime, we can plot out the current for these two nodes. As you can see, if we calculate the modulation contrast using these two currents as Nsig and Nu for MC calculation, the MC calculation for GPD-CE is 86% at 3.3 volt, while the GAPD is 75% at 3.3 volt. For different depths of electrons, we can clearly see that the electron depths are in deeper places. The modulation contrast is even better. This shows that the GPD-CE can effectively collect the carriers generated deep within the substrates and convert them into the Nsig we want. To illustrate the trade-off, the average lateral E field for this structure is calculated for region 1. Definitely, every method will have a trade-off. Our method's trade-off is that the result indicates that the average lateral E field in GPD-CE is sacrificed 30% to form the aforementioned electric field structure. Is it acceptable? Because this means that the sensitivity of our structure is lower. In my opinion, it is acceptable. This is because modulation contrast is more important than any other parameters inside this structure. The storage for signal is limited inside the chip. The sensitivity can be compensated by the integration time, but modulation contrast determines the maximum upper bound for our SNR. This slide shows the AC simulation for GPT-CE. We can see that the GPT-CE can achieve an MC value of more than 85%, even when the operating frequency is 30 MHz in the simulation. At the same time, more recombination is engaged in GPT-CE, so the MC will drop slower compared to the original one in normal processes. In addition, we also simulate the period conditions influence to the structure. We could see that in a normal CMOS process, the GPT-CE can maintain more than 80% of the MC with different period conditions. A prototype of the GPT-CE is fabricated in a TSMC 0.18 micrometer mixed signal standard CMOS process for verification. The fabricated result shows that our device achieves 83% of MC at 1 MHz, and from 1 MHz to 10 MHz, the measured MC linearly drops to 61%, and beyond 10 MHz, the MC starts to stabilize. The overall performance is about 57%. This means that our results match the simulation in low frequency, but has a 30% drop in the higher frequency. We think that this is due to potential optical equipment because it cannot generate a perfect square wave in the actual testing scene. Other reference also point out that if the optical wave is closer to a sine wave, the maximum theoretical number for MC is 64%. We also fabricated some other devices as shown in CDE figure. They include the photo gates, pin photodiode, and photo gates with large median gate. Compared to all the other structure, the GPT-CE achieves the best performance. In other works that use standard CMOS or standard FSI process, it tends to be challenging to maintain an MC larger than 50% at 20 MHz or above. In our work, we successfully achieved MC value at more than 50% at 30 MHz. In conclusion, we successfully formed an asymmetric field pattern inside the substrate, which is beneficial for collecting deep electrons. This prototype successfully achieves 83% of MC at 1 MHz and 57% at 30 MHz, closely match the simulation at low frequency and outperforming other PPD, PG, or PGM device. The results showing the strong potential for iToF sensing in massive protection. This is a fabricated chip and the testing environment. This slide shows the follow-up of this work. Later, a collaborative work with another senior student further developed this technology. We used a form dimension technology together with a new technology called Center Modulation Assisting Gate, CMAG. It can further boost our modulation contrast. What is the concept of CMAG? As shown in this figure, the CMAG will modulate in a 2 times faster compared to the normal photo gates. Therefore, the charge transfer can be boosted dynamically compared to the fixed potential. In the later testing, we can see that the CMAG successfully generates a depth map, although it doesn't look very nice because it has some problem in the modulation circuit. But CMAG achieves the best demodulation contrast compared to the normal photo gate or normal photo gate with a median gate. And this is simply the follow-up for the previous work. Let's move to my second work. As we all know, ToF are sensitive to the multipass interference signals, background noise, and short noise. These errors are correlated. Traditional filters can only tackle one of them and doing the process in the depth domain. As shown in here, in traditional ISP, the depth calculation is doing in the raw domain with simple equations. After they get the preliminary depth, they will do the post-processing in the depth domain, mainly using filters. These filters cannot tackle the correlated value. At the same time, motion artifacts has the same problem. For traditional methods shown in this figure, it is only valid for simple cases. In traditional methods, they divide motion into different cases, but for actual cases, people mainly use multiple frequencies and multiple phase. The case will be the amount of case will be very large and very complicated. Therefore, we propose to use a CNN engine to do an initial processing before the depth calculation. In our proposed architecture, we will first use the CNN engine to do a cleaning for the raw measurement. After we get the processed raw data, we will do the post-processing, such as the camera configuration, multi-frequency fusion, and calibration. We use a contest UNet to carry this task. In this UNet, most of the layers are contest to 4-bit and 8-bit, except the final layer. This UNet is trained with a flexible, large, augmentable time-of-flight dataset. This dataset includes truly depth ground truth, motions, short noise, and multipass interference in a simulation environment. In details, our CNN engine is shown in this figure. For the prototype system, a CNN accelerator together with some peripheral circuits is included. In the CNN accelerator, it contains the controllers, buffers, and the computation cores. This cores is mainly for convolution and upsample. The convolution core can successfully carry the sparsity calculation for the convolution with the index of zeros in weight. And for the upsample, we use bilinear interpolation to replace traditional deconvolution. With these two accelerations, we successfully accelerate the entire calculation by 2.78 times. Here shows the visual quality of this method. As you can see, the multipass interference, reflections, and short noise has been clearly reduced. We also test this system in real cases. As you can see, the noise we want to address is clearly suppressed, and also in motion situations, we can also achieve a better result compared to baseline. Here shows the demonstrating of the prototype system. This system is implemented on FPGA with the resources shown here. The clock frequency for this system is 200 MHz with a latency of 85.6 milliseconds if the input is 256 window size in 9 channel. The total power is 5.65 watts. Compared to the other works, we have achieved competitive accuracy. And also, compared to other hardware works, we are the first one that introduced CNN MPI and noise reduction in ISPs. I introduced my first work in a quicker way because I think some of the issue of my previous work is addressed in this work. So let's join into my third work. Nowadays, the ISP for 3D or 2D sensors can be roughly classified into 4 kinds of categories. For the first and second one, it is mainly for the traditional one using one or multiple sensors. The advantages of them is that they can run in traditional algorithm in a very fast way, and it is very simple. However, the performance, generally speaking, is not as good as the AI method. For Type C and Type D, they are mainly for the end-to-end AI ISP and multi-modality AI ISP. My previous work belong to Type C. The advantages of this kind of ISP is that it has the strong capability for AI. And the problem is the inference is very heavy. And also the generalization for AI models is challenging. For my previous method, it is highly dataset dependent. I have to say, if I adapt it into a new camera, it will require significant effort in the dataset corrections to achieve my previous result. Some of the edge works also belong to Type C and Type D. End-to-end integration of AI models tend to be tightly coupled with specific sensor configurations, limiting the reusability and scalability of the system. Meanwhile, the inflexibility and complexity are also notable for the multi-sensor fusion setup. Previous works mainly focus on two-sensor fusion or applications such as pose estimation. In our work, we want to focus on one-sensor fusion with high adaptability. Let's see in the details. If you do the two dual-sensor fusions, you may face integration and iteration challenges. First of all, you need a dedicated network for the fusion, and then you may face integration gaps such as the context difference, resolution difference, and placement difference for these two sensors. In addition, it is hard for you to iterate your method because the data set and models for RGB sensor is much more than the ToF sensor. It is hard for you to do in the iteration. In our method, we want to propose an architecture with both foundation model for AI ASIC and the flexible ISP algorithm in FPGA. Therefore, we can achieve a sensor adaptability, AI generalization ability, sensor performance, FPGA speed, and ASIC speed. What is our motivation? Every word in this passage, I think, is very important, so I will read it word by word. ToF estimation is physically reliable, but remains prone to noise, multipath interference, and reflection. Monocular depth estimation produces dense and thematically rich depth maps, but suffers from scale ambiguity and lacks physical grounding, which can lead to fatal errors in downstream tasks. Our motivation is to leverage the strength of high-fidelity ToF data and high-quality depth periods from foundation models in a monocular and zero-shot manner to generate depth maps that are both physically consistent and visually accurate, with strong generalization across diverse real-world scenarios. We have high-fidelity ToF data. Therefore, we can achieve accuracy. We have high-quality depth periods. Therefore, we can achieve perceptual quality. We run the foundation models in a monocular and zero-shot manner. We can also achieve simplicity and adaptability. Here shows an example for the same thing in ToF and MDE. At the depth line, the ToF depth is accurate, but the trend is noisy. But for MDE, the depth is ambiguous, but trend in local places is accurate. This is different for these two methods. We want to use MDE foundation model to help us bypass the intrinsic limitation of ToF. At the same time, use ToF to correct the fatal error from foundation models. Here, we use the foundation models depth anything V2 in the proposed system. Let's look at the processing detail. After we get the raw ToF pixel screen, it will first go through the triangular feature extraction. After the extraction, we can do intensity extraction and normalize it to fit it into the MDE foundation model. This model would be run in a transformer accelerator, a dedicated ASIC. During the running, we will then do the depth calculation and multi-frequency fusion. After we get these two maps, we'll try to fuse it together with our proposed ToF MDE vision transformer fusion algorithm called TMVF. The details for transformer accelerating belongs to another paper. I will not join into the detail here. So for the TMVF, we try to fuse the state-of-the-art MDE depth estimation model. Although this model is state-of-the-art, it has many fatal errors. For example, here, it recognizes a white box as a ground. I have to say, I didn't choose this map intentionally, but it is the fact that this kind of error always occurs in many cases because this foundation models is trained with linear way2. It is a segmentation model. If the segmentation is wrong, the depth is wrong. In our method, we will first do a method of momentums to correct the global discrepancy in scale and offset for the MDE and ToF. The first order and the second order of these two depth maps would be corrected in distribution, as shown in this equation. And then we will do the processing for the ToF map. Let's see a clearer example in a figure instead of these equations. What we will do, for every ToF input, if it is invalid, we will first find this valid neighborhood and record this neighborhood's position. And then we collect these corresponding MDE pixels in the same positions. After that, the mean of these two windows would be calculated. Then we minus this mean with the center of the MDE model. And this value is like a kind of relative value, and the mean of these values is the position for the start point. And therefore, we can get the final ToF value at the point we want with the start point and the local collection value. This is the final value. The idea of this method is to correct our depth map with the local depth information from ToF and the local trend for the MDE. Therefore, we can take the advantages from both sides. After that, we will try to fuse them together. With the previous step, the depth map for ToF is already, I think, much more better. But in many cases, it is not smooth. So we will fuse them to make it smoother. The detailed method is shown here. Generally speaking, the larger the difference of this map, the more confident is trusted by the VIT input. And if the difference is small, the system will try to trust the ToF map. Here, then we can get finally a map with a good value and trend. Let's look at the examples and you will understand. Here shows a zero-shot conceptual example from a flat data set. This is the MDE model output, and this is the ToF output, and this is the final fusion output. As you can see, the error for MDE map is not large for every pixel, but it occurs at every places. For the ToF, there are many clean places, but also many places with larger noise. After our fusion, we do not have very large errors, and also for most of the places, error is small. This is our idea. After we get the TMVF algorithm, run it is also very important. We designed 3 modules to run this entire architecture. It includes a unified statistics unit, global alignment module, and the local alignment module. For the global alignment module, it will reuse the USU unit and do the MOM calculation. After that, it goes into the local alignment modules. This local alignment module is fully stream oriented, and the working is pipeline. As you can see, we use line buffers to do the process. For the entire design, we do emphasis on the modularity and scalability, facilitating seamless integration into high-throughput visual processing. With this architecture, we can achieve a low latency operation and high resource efficiency to render it for real-time depth enhancement on FPGA. Let's look at the perceptual evaluation. This is a zero-shot evaluation from 3 different data sources. It includes the flat dataset, the TICAM dataset, and the real data collected by us. Actually, the real data from us is the most challenging one because I intentionally choose the hardest one. As you can see, for all the data, we have achieved a very good performance. No matter the ToF data is noisy or wholly or reflective, or the MDE is off-scale, overexposed, ambiguous, or others. All the problems are solved in our method. Somebody may ask that there are some matrix-based version for the MDE model. Is it okay to use it directly? I have to say no, because as you can see, the matrix version exhibits exactly the same problem compared to the previous disparity one. So it cannot solve the problem of the MDE. Compared with other in flat dataset, our work can achieve a competitive MAE, mean average error, in a zero-shot manner. Why is it always the flat dataset? Actually, I also don't want to use it. But to evaluate our iToF ISP method, we have to get an entire ISP pipeline, but not the depth directly. Currently, we only have flat to do the evaluation with ground truth and also the raw data. Even in this case, we can see that compared to the sole method, the TMVF can achieve 43.8% MAE compared to the previous one, previous ToF one, and also the 26% SSIM improvement compared to the single ToF. We have achieved good accuracy and good SSIM. And here shows the demo of the architecture. If we compare our work with other works, the most large difference for our works is a 10 times higher computation complexity with 27.6 GOPS per frame compared to previous works. This reflects the substantial increase in model generalization and adaptability brought by adopting the state-of-the-art vision transformer-based architecture in contrast to the conventional lightweight CNNs. Although large model do not mean better performance, but generally speaking, larger is better, right? Let's go back to our motivation. We have high fidelity ToF data, high quality depth periods, foundation models in molecular manner, and foundation models in zero-shot manner. Accuracy, perception quality, and simplicity and adaptability are achieved simultaneously. Finally, we have achieved a real reliable method for the real world. Thanks for your listening. This is the end of my presentation. Thank you.